So this is the setup for the first of two buoyancy experiments I'll be doing. A water bottle as the container, and a camera mounted onto the reference frames that I'll be accelerating, which is the dolly. The reason why we have to constantly accelerate to recreate buoyancy is because we're connected to the Earth, which is already in constant motion, and in order to overcome constant motion, you need constant acceleration. As you can see, the air bubble is centered, which means the bottle is level and at rest. The air bubble will always be displaced or pushed relative to the motion of the bottle. When I accelerate the bottle, the pressure of the bottle pressing on the water creates a pressure gradient. The water is then able to push anything that's less dense, like the air bubble, in the direction of acceleration, which is what we will call buoyancy. You can't have buoyancy without a pressure gradient, and you can't have a pressure gradient without a contained system that's in motion. For the second buoyancy experiment, I have a cargo van as the container, a helium balloon, and an apple. I also have the camera mounted onto the reference frame that I'll be accelerating. As soon as I accelerate, the pressure of the van pressing on the air creates a pressure gradient, with the most dense air towards the back of acceleration and the less dense air towards the front. The air is then able to push the helium in the direction of acceleration because it's less dense, but the air cannot push the apple because it's more dense, therefore the apple remains at rest. The apple only appears to move in the opposite direction of acceleration because the camera is also moving with the reference frame. The helium balloon has true motion and the apple has apparent motion. In order for the Earth to be motionless, you need a force moving in opposite directions at the same time to be able to accelerate the apple in one direction and push the air and helium in the opposite direction without any motion of the container. You would also need this same force to accelerate a container without any displacement or buoyancy. In other words, you have to believe in a magical force that can accelerate a container without any pressure or buoyancy, and also be able to create pressure and buoyancy in a motionless container, which is the literal opposite of what physics shows. Physics proves that you can't have pressure and buoyancy without motion of a container, and you can't have motion of a container without pressure and buoyancy, proving that the Earth cannot be a motionless plane.
Help keep all your passwords safe.
It is a simple fact that air and water will always displace under conditions of acceleration. This is observable, measurable, testable, and repeatable. You can recreate this for yourself. The air bubble will always be pushed in the direction of acceleration 100% of the time. If you claim acceleration in freefall, the air bubble should be pushed down in the alleged direction of acceleration. However, the air bubble shows a constant motion up when connected to the Earth, and a deceleration up in freefall, which is the opposite direction of the alleged acceleration, proving that the bottle is not accelerating down, it's decelerating. When I actually accelerate the bottle down, the air bubble also gets pushed down in the direction of acceleration. I'm only able to accelerate down for a brief second because I'm also connected to the Earth. In order to overcome constant motion, you need constant acceleration. A slinky will only stretch when there is a force being applied. You can test this for yourself. You cannot stretch the slinky without a force. This is something important to note as it will make the following experiment much easier to understand. When we have a bottle with water and it's connected to the Earth, we can experience weight and buoyancy, which are effects of a force or motion. For example, something that's more dense or heavier than the water by volume, like the slinky, will sink or appear to go down, and something that's less dense, like the ping pong ball, will get pushed to the top or float. If I glue the ping pong ball to the top of the slinky so it can be one unit, we can experience a density gradient. The more dense material at the bottom and the less dense at the top. Also, the fact that the slinky is being stretched shows that there is a force present when connected to the Earth. However, as soon as I release the bottle into freefall, the buoyant force of the ping pong ball and the weight of the slinky completely vanish along with the density gradient. The slinky is no longer at the bottom and the ping pong ball is no longer at the top. Also, the fact that the slinky is not being stretched shows that there's no force present. Acceleration requires a force. No force in freefall equals no acceleration in freefall. A simple accelerometer is a container with air and water because solids, liquids, and gas will always displace under conditions of acceleration or when there is a force present. The water will always appear to move towards the back of the container and push the air towards the front. In other words, the air will always get pushed in the direction of acceleration 100% of the time. When we're observing objects appear to move in a particular direction, vision alone is not a physical measurement of acceleration. For example, when I have a ruler going through a box, whether I move the box or whether I move the ruler is always going to appear to move because the camera is connected to the box. Unless we can observe it from the outside, the ruler will always appear to move. However, if I was to attach a simple accelerometer to the ruler, then we will know if it's the ruler moving or the reference frame without having to observe it from the outside. Which ruler would you bet is the one accelerating? 1 or 2? So when we're talking about downwards acceleration, which bottle will you bet is the one accelerating? 1 or 2? So in this experiment, I'll be using a slinky, a helium balloon tied to the slinky, and a box as the container. I cut a hole on the box and put clear tape so when the box is closed, we'll still be able to get good lighting inside. I also cut a small hole to be able to mount my camera. As you can see, when the box is connected to the earth, there is a force present. We can experience buoyancy. The helium balloon is being pushed to the top because it's less dense than the air. You can measure the balloon's buoyant force with the slinky that's being stretched. However, the instant I release the container into freefall and it's no longer connected to the earth, buoyancy completely vanishes. The air is no longer pushing the helium balloon up. You can measure that the balloon's buoyant force is no longer present by the fact that the slinky is not being stretched. This experiment shows that the upwards force is only present when connected to the earth, proving that the earth's upwards motion is the cause for what we call buoyancy. Buoyancy is not a cause of itself and requires an external force.
Whether you hold it in, let it out, or whatever this is,
In this experiment, I'll be using a rock, a compression spring, and a retention spring. It is a simple fact to note that a force is required to either compress a compression spring or stretch a retention spring. The springs cannot compress or stretch on their own. For the first drop test, I taped the compression spring onto the reference frame so it doesn't move around. I also taped the camera as low as possible to get a better view of the spring. When connected to the earth, the rock weighs about 2 pounds and it's able to compress the spring all the way down. The spring wants to push up on the rock, but the resistance or weight of the rock is greater. However, the instant I release the reference frame into freefall, the weight of the rock completely vanishes and the spring is able to push the rock up. This experiment shows that the weight of the rock is only a factor when connected to the earth. For the second drop test, I hung the rock and retention spring from a screw I drilled at the top. As you can see, when connected to the earth, the weight of the rock is able to stretch the spring, showing that there is a force present. However, in freefall, the weight of the rock completely vanishes and the spring returns to its original shape, swinging the rock up, showing that there isn't a force present. Weight is not a property of matter and requires an external force, which is only present when connected to the earth. Observable, measurable, testable, and repeatable. In this experiment, I'll just be using a water bottle. I drilled 3 holes vertically on the side to measure the difference of the water pressure when it's filled. When the bottle is filled with water and connected to the earth, we can detect that there is a force present. We know that there is a force present because the water has pressure, weight, and it's being pushed out of the holes. The water cannot create pressure, weight, or push itself without an external force. We can also see that the water is being pushed out of the 3 holes with 3 different pressures, showing that there is a pressure gradient. The first hole at the top is experiencing the least amount of pressure from the 3 because it has the least amount of mass or weight above it pushing down, which causes the water to be pushed out of the hole the shortest distance. The second hole to the bottom is experiencing more pressure than the first hole because it has more mass or weight above it pushing down. Therefore, the water is being pushed out further. The third hole at the bottom is experiencing the most amount of pressure from the three because it has the most amount of mass or weight above it pushing down, which causes the water to be pushed out the furthest. However, as soon as I release the water bottle into freefall, the pressure gradient or weight column completely vanishes and is no longer pushing the water out of the holes, showing that there isn't a force present. No force in freefall means there's no acceleration. In this video, I'll be doing two different density and buoyancy experiments. I'll be recreating density and buoyancy in three different vectors utilizing motion of a contained reference frame. In the first experiment, I'll be using a container with water, a red ping pong ball, and a steel ball. The ping pong ball and the steel ball will always displace relative to the direction of the force that's applied. For example, when I accelerate the container to the right, the container pushes the water in the same direction, creating a pressure gradient. The water is then able to push anything that's less dense, like the ping pong ball, in that same direction. That is what we would call buoyancy. However, the water is not dense enough to push the steel ball like the ping pong ball, so the steel ball remains in the same position. The steel ball only appears to move in the opposite direction of the buoyant force because the camera is also moving with the container. The ping pong ball has true motion and the steel ball has apparent motion. The same principles apply when I accelerate in any other direction. In the second experiment, I'll be using a tube with water, an air bubble, and a steel ball. To accelerate the container down, I will be using a resistance band. As you can see, when connected to the earth, we can experience a force creating density and buoyancy. The air bubble is being pushed up and the steel ball appears to move down in the opposite direction of the buoyant force. You can also see the air bubble is flattened where the force is being applied. However, when I release the container into freefall, density and buoyancy completely vanish. The air bubble is no longer being pushed up and turns into a sphere, showing that there isn't a force present in freefall. When I actually accelerate the container down, we can see density and buoyancy invert. The air bubble is being pushed down and the steel ball appears to move up. Not only does acceleration require a force, acceleration will always cause displacement of solids, liquids, and gas, proving that objects don't accelerate down in freefall. A digital accelerometer is a device that detects the presence of a force or acceleration. For example, when at rest and connected to the earth, it detects 1 g-force. As soon as I accelerate it from being at rest, the accelerometer detects that acceleration by increasing the g-force. Whether I accelerate it to the right, to the left, up, or down, the accelerometer will always detect the acceleration 100% of the time. However, the instant I put the accelerometer into freefall, it detects a deceleration. It goes from 1 g down to 0. If the accelerometer was accelerating down in freefall, it would detect that acceleration by increasing from 1 g, not decreasing. Not only does the accelerometer show that there's no detectable acceleration in freefall, it also shows that the vector or force of the Earth is up. When I switch to the vector tab of the accelerometer, we can see when at rest on Earth, it detects that the vector or force is down, as shown by the green line. However, the vector on the phone is inverted because when I apply a force to the right, the vector goes to the left. And when I apply a force to the left, the vector goes to the right. When I apply a force down, the vector inverts up. And when I apply a force up, the downwards vector increases, showing that the vector on the phone is inverted from the true direction of the force, or vector. So when the phone is at rest on the earth and knowing that the vector is inverted, the direction of the force or vector is up. Also, when the accelerometer is in free fall, the vector completely vanishes, showing that it's not being accelerated down by any force. Which proves that the force or vector of the earth is up, not down. In this video, I'll be showing that flames always follow the direction of the force. Flames are less dense than air, so depending on the direction of the force pushing on the air, that will also determine what direction the flames get pushed. For example, when I have a flame in a container with air surrounding it, as soon as I apply a force to the right, there's a greater compression of air to the left that is then able to push anything that's less dense, like the flame, in the same direction as the force. When I apply a force to the left, the greater compression of air to the right is then able to push the flame to the left. This can be demonstrated and repeated 100% of the time. The flame will always get pushed in the same direction as the force. When I actually apply a force down, we can see the greater compression of air switch to the top of the container, pushing the flame down, showing that there is a force present. However, when I release the container into free fall, there is no compression of air in the container, so the flame is not being pushed in any direction and thus turns into a sphere, showing that there isn't a force present. The compression of air in the container is only present when connected to the earth, pushing the flame up, showing that the force of the earth is also up. You can't have acceleration without a force, and you can't have a force without any reaction of the flame.